All right, this video is going to be about 12 to 14 minutes long, and it's intended to cover the section of your lecture workbook that is on page 141, and it covers the phase diagram. So if you please, would you turn to page 141 in your lecture workbooks? And we're going to work through this right now. If you don't have access to your lecture workbook, then this is not going to, you're not going to have access to this image to be able to write in your lecture workbook, but I have a solution for that. And so I am now sharing the image from your lecture workbook. Can everyone see that? Hopefully you can see that. If you cannot see that, let me know in chat. Okay, so this section is in the chapter that we're talking about IMFs, intermolecular forces. We're just talking about phase changes, changing from one physical state or phase to another. And then we get to this section C. So let's fill in some gaps here, and then we'll talk about this graph right here. A substance's phase or physical state depends on two properties. The first property is pressure, and the second property is temperature. And then we can graph a substance's pressure and temperature on a phase diagram. And the phase diagram, as you'll see, graphs the pressure on the y-axis, the temperature on the x-axis. And then for every data point in here, we can mark down what the physical state is or what the phase is for that substance. So I've given you an example here, and this is the phase diagram for water. And there are a couple of reasons that I've given you the phase diagram for water. One is that water is one of the most common chemicals that we will encounter. We are mostly made up of water. And the other is that there is a particular rarity in the phase diagram of water that I want to draw your attention to, and it has to do with this line that I'm pointing to right here, between the solid and liquid phase. We'll talk about that more in just a moment. So, some things I want to point out about this phase diagram. First of all, every substance has its own phase diagram. This is the phase diagram for water, but every chemical substance will have its own unique phase diagram. So if you have a block of a bar of gold, it will have its own phase diagram. If you have carbon dioxide, it will have its own phase diagram. So you get the idea? So this is the phase diagram for water, and there's some elements of this that I want to point out to you. First of all, we have regions in this diagram, in this chart, in this graph, where we have solid, liquid, and gas. Now, if we didn't know what water was and we weren't familiar with what water was, we could look at this phase diagram and it would tell us the physical state that water would be in depending on its pressure and temperature. So as an example, we look at the pressure here and we say, well, let's assume that we're under 1 atmosphere of pressure, which is what you and I are approximately under right now, 1 atmosphere of pressure, a little bit less, because we're not at sea level. So we're a little bit less than 1 atmosphere, but we'll call it 1 atmosphere. And let's say that we were approximately at 30 or so degrees Celsius. That's a warm day. Now, you and I intuitively know what physical state water is going to be in, right? On a warm day, water is going to be in its liquid state, right? But if we didn't know that, we could take a look at the pressure, 1 atmosphere, and approximately 30 degrees Celsius. And we could see where that data point would be, and it would be right here in this block of liquid water. So that's how you basically use the phase diagram to predict or to determine the physical state of a substance, right? There are a few key features about this phase diagram that I want to point out to you. First of all, when we have a boundary, a line drawn between two physical states, those boundaries designate the data points, the sets of pressure and temperature at which these two states are in equilibrium. So for example, if we are at 1 atmosphere of pressure and 100 degrees Celsius, notice that we fall right on that line. That means that we are at a phase boundary. So the liquid and gas phases are in equilibrium with each other. That's the boiling point of water, right, at 1 atmosphere? So you would expect to see both liquid water and water vapor in an equilibrium, interconverting at that stage. And that's what you see if you have a pot of water and it's at 1 atmosphere and 100 degrees Celsius. You have liquid in the pot and vapor coming off of it. So that's what a phase boundary is. It's when you have these two physical states that are in equilibrium with each other. And that brings to mind this term right here, the triple point. So the triple point is what's going to go in this gap right here. So the triple point is the temperature and pressure at which all three phases or states are in equilibrium with each other. So if you had the temperature and pressure such that the water was right here, then you would see solid water, which was ice. You would see liquid water, and you would see water vapor all at that point. They would all be present. So there's a question here. At what temperature and pressure does this occur for water? Well, you can see I've drawn it here. The temperature is 0.01 degrees Celsius, and the pressure is 0.006 atmospheres. Okay? That's called the triple point. Triple, 3, right? All three phases are in equilibrium with each other. How are we doing? Do we have any questions? Anybody want to put a question in the chat? Any questions about what I've mentioned so far? Doing all right? Okay, we'll continue on. So that's the triple point. Now, if we follow this this boundary all the way up, here to the upper right, we see the critical point. The critical point is what goes in this gap here. The critical point. The critical point is the point above which, that is the temperature and pressure above which, the liquid and gas phases can no longer be distinguished from each other. So let me explain what that means. You know that if you have a liquid and you increase the temperature generally, let's say you have a liquid and the temperature and pressure is out here somewhere. If I increase the temperature by moving rightward across this graph, what's going to happen? That liquid water is going to cross the phase boundary and suddenly start boiling, right? It'll turn into a vapor. So this can happen in the opposite direction too. If I have a vapor and I start to decrease the temperature by moving leftward, I'll turn it into a liquid. And then eventually decrease the temperature enough and it turns into a solid, right? That's fairly intuitive. We understand that. But there is a temperature and pressure at which the pressure is so great and the temperature is so great that the chemical substance cannot neatly make a transition from one phase to the other. So you're adding so much temperature that it wants to vaporize, but you're keeping it under such pressure that it can't do that. And so you have both liquid and vapor that are together, and they can't be distinguished separate from each other. And we call that the critical point. So if you have water that has a higher pressure than 225 atmospheres and a higher temperature than 374 degrees Celsius, you have met or exceeded that critical point. and you have what is called a supercritical fluid. And again, that supercritical fluid, that's what goes in this gap. Supercritical fluid, that is a fluid at which you can no longer distinguish the liquid and the gas phase from each other. They're both together. They're so hot, it's so hot that it's trying to vaporize, but it's under such great pressure that it's not permitted to. And so it's a strange phase quality that has both liquid and vapor properties, gas properties, called a supercritical fluid. All right, are there any questions about that? It's not exactly the same as a plasma. A plasma is a fairly different sort of phase. Plasmas, typically we're talking about things like when you have ionized gases, and in those cases we don't have a liquid phase present at all. Yeah. So that's why we call it a supercritical fluid. Other questions? All right, so this was a fairly quick little section here. There are no problems to work out except some text to be able to add for vocabulary. But I wanted you to be able to recognize a phase diagram. Now here's the odd thing with water, that this doesn't happen with most other chemical substances. Does everybody see this line right here, the phase boundary between the solid and liquid? What slope is that? Does that have a positive or negative slope, that line right there? If you look just at that phase boundary, is that a positive or negative slope to that line? That's right, it's a negative slope there. Having a negative slope to the phase boundary between solid and liquid is very uncommon. It happens very, very rarely, and it happens with water as one of the rarities. And I'll explain why this is important. And it gets back to why water is less dense as a solid than when it's a liquid. So let's imagine that you have a sample of water that's right down here where my cursor is. It's a solid, right? Right here where the tip of my cursor is. And I am going to increase the pressure. So it is a solid already, right? Now, if you had a solid bar of gold, right, and you increased the pressure on it, increasing the pressure favors the smaller volume, right? Because as you increase pressure, you're trying to crush it down. So typically when you increase the pressure on a substance, it wants to solidify and become the most dense possible form, right? Because you're putting it under pressure and trying to reduce its volume. Well, look what happens to water when I increase the pressure on solid water. And I move up this scale, increasing the pressure, going up, 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 up. And look what happens. I cross the phase boundary and suddenly the water sample liquefies. That is very uncommon. It's very uncommon to add pressure to a solid and have it turn into a liquid. For most other substances, the slope of this grade boundary, the slope of this phase boundary is a positive slope. So it would be going like this in a positive slope direction, which means that once you have a solid, you can increase the pressure all you wanted and it would never turn into a liquid. But water is odd this way. And remember that this gets back to why water is less dense as a solid. Because when you have these water molecules and they're slip sliding past each other as a liquid, then when they start to freeze into a solid form, those water molecules form a network, a lattice, a crystalline lattice. It's a molecular crystal, and there are gaps in that molecular crystal that did not exist when it was a liquid. And because of those gaps in the solid crystal of ice, the ice is less dense as a solid. than water. So when we pressurize a block of ice, it favors the more dense liquid, which is a very odd thing. So most substances don't do that. And we can see it right here in the slope of this phase boundary right here. Okay? So that's all I wanted to share with you. And I will go ahead and stop the recording of this video, and then I'll post it to YouTube so it will be available for you.